So from now on, we will assume that the system Ax equals b has no redundant equations. So what does that mean? So basically we can assume that the system has no redundant equations, and if the system does have redundant equations, then we said that we can remove them without changing the system. So as a result, if the system does have redundant equations, we assume that we have already removed them. So as a result, we can assume that the system has no redundant equations. So in particular, this implies that well, if the system has no redundant equations, then what can I say? So if you think of the examples that we did on Monday, so that means that there are no linearly dependent rows, basically. Okay, all the linearly dependent rows have been eliminated. So which means that all the rows are linearly independent, which means that the rank of the matrix is the same as the number of rows. So the rank of A is equal to m, basically, okay? So we always assume that n is at least as large as m. So there's at least as many equations as there are unknowns, okay? So in particular, this assumption implies that rank of A is equal to m. And if you look at your notes from last time, if the rank of A is equal to m, that means that for every choice of right-hand side vector b, there is a solution, right? Okay? All right, so now we're going to define basic solutions in this context. And this is a very simple definition. So consider the system Ax equals b. Where, again, A is an m by n matrix. B is an m-dimensional vector of right-hand sides, and X is an n-dimensional vector of unknowns. And we're going to assume that rank of A is equal to m. So basically, we assume that the system has no redundant equations, basically. So we're going to do the following steps. So we're going to pick m variables from x1, x2, all the way up to xn, such that the columns of A are corresponding to these m variables are linearly independent. Does everyone remember what linearly independent means? So essentially it means that none of the columns can be written as a linear combination of other columns, basically, right? All right, so we have n variables and we have m equations, and we assume that the number of variables n is at least as large as m, so n is greater than or equal to m. And we assume that the rank of A is equal to m as well. So in the first step, out of a total of n variables, we're going to pick m of them, okay? But we're going to do this in a careful way, so we're going to do it in such a way that the columns of A corresponding to these m variables are linearly independent. What does that mean? Well, remember from linear algebra that the rank of, you have the row rank of a matrix, right? So which is the largest number of linearly independent rows, basically. And you also have the column rank of a matrix, right? So that's the largest number of linearly independent columns. And one of the fundamental results in linear algebra says that the row rank is the same as the column rank, basically, right? Right? Okay. So which means that if the rank of A is equal to m, then that means that A has m linearly independent rows, okay? And it also means that A has m linearly independent columns as well, right? Okay? So basically what I'm going to do is I'm going to pick m linearly independent columns of m, and I'm going to look at the corresponding variables, okay? I'm going to give you examples in a minute. So in the second step, I'm going to rearrange the columns of A so that these m variables are listed first. So what does that mean? Basically, we have the system AX equals B. Okay. Then what I'm going to do is I'm going to rearrange my variables. I'm going to call them XB and XN. And I have the right-hand side. And underneath XB, I'm going to have the columns of A, which I'm going to call matrix B. And underneath XN, I'm going to have the columns of A, which I'm going to call N. And the right-hand side B. So as a result, I can write the system as follows. So I'm going to have Bn multiplied by XB XN. And the right-hand side value is equal to B. I'm going to give you an example in a minute, so hopefully you'll see what I mean by this better. So, all right, so now let's focus on the matrix B. So how many rows does B have? What's the number of rows of B? So it's the same as A, basically, right? So number of rows of B is the same as number of rows of A, so B has m rows. How many columns does B have? Well, so remember, I'm actually picking m variables, right? From x1 through xn. So basically, these are my m variables that I pick. Okay? So I'm listing them first. So how many columns does B have then? The same as number of variables, basically, right? So since we have m variables, then we have m columns as well. So this implies that B is a square matrix. So B has m rows and m columns. Okay? So what else do I know about B? Well, remember the way I picked the columns of A was such that the columns corresponding to those variables were linearly independent, basically, right? Okay? So which means that the columns of B have to be linearly independent. Okay? So B has m columns. Okay? And B also has m rows. So what can I say about the matrix B then? So if I have a square matrix and if all the columns are linearly independent, so this means that B is an invertible matrix, basically, okay? So if B is a square matrix and if all the columns are linearly independent, then B is invertible. Okay, so you can actually invert the matrix B. All right, in the third step, so we're going to set each of the n minus m variables in xn to 0 and solve for only the m variables xb. And the m variables in xb. So what does this mean? Well, essentially, so I rearrange my system so that it looks like the following. So I have Bn multiplied by xb xn is equal to B. So here I have m rows. Here I have m columns. How many columns does n have? So A has n columns overall, right? And I'm singling out m columns first. So n corresponds to the remaining columns, basically, right? So how many columns does n have? Exactly. So it's m minus m, right? This is not too hard. So this has only m minus m columns, so that the total number of columns is equal to n, basically. Okay. How many variables does xp have? So how many variables are there in xp? So there are only m variables in xp, right? Okay. How many variables are there in xn? Exactly. So the number of variables in xn is n minus m, and b again is an m-dimensional vector. Okay. So basically, if you just write this out as the matrix vector product, you're going to see that all the dimensions work out nicely. So I can write this as follows. b times xp plus n times xn is equal to b. Okay? Then what am I going to do? Well, I'm going to set xn to the 0. So this is basically the 0 vector. Okay, it's not a constant because xn has n minus m components. So I'm setting each of them equal to 0. Well, if xn is equal to 0, then this system simplifies. So I can write this as b times xp is equal to little b, basically, right? All right, so now this system has m rows and m columns. So basically the number of rows and number of columns is the same, or number of equations and number of variables is the same. And furthermore, we know that B is an invertible matrix. Okay? So how can I solve for this system? You took linear algebra, right? So xp is exactly equal to b inverse b, right? Okay? So as a result, what we do is the following. I start with the system ax equals b. I rearrange my variables as xp and xn. Then I set xn to 0, and I solve for xp. And if you think about this a little bit, so basically I have a solution, right? So the xp component is equal to b inverse b, and the xn component is equal to 0. So this gives me a system, this gives me a solution to the original system ax equals b. Okay? So this is one way of obtaining a solution. Step number 4. So variables in xp are called basic variables. And similarly, variables in xn are called non-basic variables. Okay? So I'm going to give you an example, and hopefully this is going to be a bit clearer. So here's an example. So let's recall example number 3, but without the redundant equation. So we have the following equations. x1 plus 2x2 plus x3 is equal to 4. And then x2 minus x3 is equal to 1. Okay, so we have 2 equations and 3 unknowns. All right, so first of all, let's figure out what my matrix A is. So what's my A matrix in this case? So it's going to be 1, 2, 1. So 0, 1, minus 1. My x is given by x1, x2, x3. And my right-hand side vector b will be given by 4 and 1. Okay? So if I go back to my sort of general description, what is m in this case? So m is the number of equations. M is equal to 2. What about n? N is the number of unknowns. So n will be equal to 3, right? So basically, m is equal to 2 and n is equal to 3. And what's the rank of A in this case?
2.
Well, both rows are linearly independent, so as a result, the row rank is equal to 2, but that's the same as the column rank. So as a result, the rank of A is equal to 2, which is the same as m, basically. Okay, so it satisfies our assumptions. So here's what we do. So first of all, I'm going to pick 2 variables because we have 2 equations only. Okay? So the number of variables I'm going to pick will be the same as the number of equations. So I'm going to pick 2 variables, and let's pick x1 and x2 as my basic variables. Okay? Then my non-basic variable will be equal to x3. Okay? So the number of basic variables should be the same as number of equations, basically. Okay? All right, so then what I'm going to do is I'm going to look at the corresponding matrix B. Now, how is the matrix P defined? Well, it's pretty easy actually. So what you do is, so this is the column corresponding to x1, this is the column corresponding to x2, and this is the column corresponding to x3, basically, right? Okay? So I'm going to only look at the columns corresponding to x1 and x2, so which are 1, 0, and 2, 1. Okay? And this is going to be my B matrix. Note that B is a 2 by 2 matrix, right? It's a square matrix, basically. Okay? So what's my N matrix in this case? So N corresponds to the column corresponding to non-basic variables, but we have only one of them, so the N matrix will be given by 1 minus 1. Okay? All right, so now I'm going to apply that procedure over there. I'm going to set all the non-basic variables to 0. Okay, in this case, we have only one of them. So xn, which is equal to x3, will be equal to 0. Okay? So now I'm going to solve for only x1 and x2. Okay, so how can I solve for x1 and x2? Well, if I set x3 equal to 0, then basically this part of the equation disappears, basically, right? So the third column disappears. Okay? So now I have two equations and two unknowns. Okay, and I know how to solve this system, right? So basically, now I'm going to look at xp, and xp is given by x1 and x2, and I'm going to use that formula over there. So I'm going to take the inverse of this matrix, and then multiply this by little b, basically, right? Okay. So what's the inverse of b? And I'm going to multiply this by little b. Okay? So what do we obtain? Well, the first component is equal to so the first component is 2. What about the second one? The second one is 1. Okay? So essentially, I have a solution to my system. x1 is equal to 2, x2 is equal to 1, and x3 is equal to 0. Okay? And indeed, if you plug in these values into the original system, you're going to see that all the equations are satisfied. Okay? Now, this is a sort of specific solution, so we call this a basic solution. Okay? So the basic variables are x1 and x2, and the non-basic variable in this case is equal to x3. The non-basic variable is equal to 0, and the basic variables have values 2 and 1 respectively. Okay? So this is one way of solving the system, basically. Okay? So it gives you a specific solution, and we call this solution a basic solution, basically. So this is a basic solution. I'm going to give you one more example. So suppose that now I'm going to pick a different sort of set of basic variables, and I'm going to pick my basic variables to be x1 and x3. Okay? Now, what is my non-basic variable then? So it's going to be equal to x2 only. Okay? What's my matrix B? Well, you're going to look at the first basic variable, which is x1, and you're going to look at the first column corresponding to x1. So it's going to be 1, 0. Then your second basic variable is x3, so you're going to look at the column of A corresponding to x3. Okay? So we have 1 and minus 1. Now, what is my N matrix in this case?
2, 1.
So N is given by the second column of A, so it's going to be 2, 1. Okay? So first of all, I'm going to set all the non-basic variables to 0. So xn, which is equal to x2, will be equal to 0. And I'm going to solve only for basic variables. So it's given by x1 and x3. So this is the same as B inverse times B. Now, what is B inverse in this case? So 1 minus 1, 0 and minus 1, right?
Yani değişmiyor mu hocam? 1 minus 1. Tamam, yer değiştirmedi şey. Minus 1.
Minus 1, 1.
Minus 1.
Minus 1, minus 1.
Minus 1,
1.
minus 1,
Evet.
0.
0.
Minus 1, minus 1,
0, 1.
0, 1. Is that right? No, that's not right.
A ile D'nin yerini değiştir, B ile C'nin işaretlerini değiştir.
Evet öyle hocam. Değil miydi? Ben de hocayı
Üsttekine bakarız.
Üsttekine bakamazsın. Üsttekinde bir aynı.
Yani değiştirecek.
Okay, so, you know, it doesn't matter basically what the inverse is. So what's important is that, so, you know, you basically have two equations and two unknowns again, okay? So your basic variables are x1 and x3. So you're going to solve the system x1 plus x3 is equal to 4 and minus x3 is equal to 1, okay? So which implies that x3 should be equal to minus 1. Okay, I'll just write the solution. And if x3 is equal to minus 1, then x1 should be equal to 5, I guess, right? Right. So as a result, basically, you know, another solution would be given by the following. x1 is equal to 5, x2 is equal to 0, and x3 is equal to minus 1. So this would be a different basic solution. I mean, the main idea is that, so it's a very simple sort of concept. So essentially, you know, you pick the same number of variables as the number of equations. Then you form your B matrix. Then you set all the remaining variables to 0. And you only solve for these variables, which we call basic variables. And this gives you a solution. And the resulting solution is called a basic solution, basically. Okay? Is the idea clear at least? I mean, so. Okay. So now let's sort of go back to LP again. So we diverted a little bit. So what's the relationship within linear programming? And I'm going to try to illustrate this on an example. So this is example number 5. So let's consider the following feasible region. So let's say x1 plus x2 is less than or equal to 6, x2 is less than or equal to 3, and x1 and x2 are non-negative. So right now I just have a feasible region because essentially what I'm trying to do is I'm trying to somehow get a characterization of corner points in terms of basic solutions. Okay? So I don't care about the objective function right now because the objective function has no role in terms of corner points. So I can draw the feasible region. So this is my first constraint. Goes through 6 and 6. And the origin is feasible, so this is the correct side. The second constraint, what does second constraint look like? Yeah, so it's a horizontal line that goes through 3. So basically, this is the second constraint. And which side should I pick? I should pick this side. Then I have non-negative 2 of x1 and x2. And essentially, this is my feasible region, right, for this example. So now what I'm going to do is I'm going to try to sort of illustrate that the corner points in this example and basic solutions are related to one another. Okay, so I'm going to sort of try to show that that's the case. So to do that, the first step is to convert this into standard form. Okay, so right now this problem is not in standard form. Okay, so what was the definition of standard form? Basically, all the variables should be non-negative, which is the case for this example, so that's okay. So we should have equality constraints. We don't have them right now, so we have to convert these two constraints to equality constraints. And the right-hand side should be non-negative. That's also okay. So the only problem is we don't have equality constraints for this case, right? So we just need to convert it into equality constraints. So how do we do that? So what was our procedure to turn a less than or equal to constraint into equality constraint? Exactly. So we're going to stack variables. So I'm going to call it x3. And the right-hand side now becomes inequality. And then For the second one, again, we're going to do the same thing. So I'm going to add a second select variable. I'm going to call it x4. Then each of the variables should be non-negative. Okay? So now the problem is in standard form. Okay? So now, if you sort of ignore the non-negativity constraints, we have AX equals B basically, right? So this is my system AX equals B. So what's my A matrix in this case? So it has 2 rows and 4 columns. So I'm going to have 1, 1, 1, 0, and then 0, 1, 0, 1, right? So this is my A matrix. My X vector will be given by X1, X2, X3, and X4. And what's my right-hand side vector B? 6 and 3, exactly. Okay? So now what I'm going to do is I'm going to look at different choice of basic variables. Okay? So just like we did in this example. So first of all, I'm going to start with x1 and x2 as my basic variables. Then my non-basic variables are x3 and x4. Okay, so what's my matrix B in this case for this choice of basic variables? 1, 0, 1, 1. So the first 2 columns of A. What about n? So it's the last 2 columns of A. So it's 1, 0, and 0, 1. Okay. Now, are the columns of B linearly independent in this case? Yes, it is. So basically, B is invertible. So this is a valid choice of basic variables. Okay, that's good. So I'm going to set xn to 0. Xn, which is x3 and x4, I'm going to set them equal to 0. And I'm going to solve for xp. And xp is given by b inverse times little b. Okay? So what's the inverse of b? Well, so it's given by 1, 0, minus 1, 1. I'm going to multiply it by little b. And little b is 6 and 3. Okay, so what do I get? So I get 3 as the first component. And 3 as the second component, right? And this is equal to my x1 and x2. Okay? So what's my solution then? x1 is equal to 3, x2 is equal to 3, x3 is equal to 4, and x4 is equal to 4, basically. X4 is equal to 0, okay? So we have x1 is equal to 3, x2 is equal to 3, x3 is equal to 0, and x4 is equal to 0. Now, since each xi is greater than or equal to 0, right? So far we ignored the equality constraints. Sorry. We ignored non-negativity constraints, basically. But it turns out that in the solution, each xi is non-negative already, right? So essentially, the non-negativity constraints are automatically satisfied. So this is a feasible solution. It's a feasible solution for these constraints, basically. Okay? So in this case, we call it, so such a solution is called, a basic feasible solution. So from now on, we're going to use BFS for short. So it's a basic solution, and it's a feasible solution at the same time. So in that case, we just combine the two, and we say that it's a basic feasible solution. Now let me go back to this picture. So what does this solution correspond to in the original problem? So let's think about that a little bit. So I know that these two systems are related, right, to one another, basically. So we discussed this before. So every feasible solution here corresponds to a feasible solution here, and vice versa, right? So there's a one-to-one correspondence between feasible solutions. And now what I've done so far is I found a feasible solution for this system. Okay? But I know that if I simply get rid of x3 and x4 components, then that gives me a feasible solution for this system as well, right? Okay? So if I look at only x1 and x2 components, I get 3, 3. Let me just go back to this picture. So what does 3, 3 correspond to in this picture? Well, it's exactly this point right here, basically, okay? So let me call that 1. So that basic feasible solution essentially corresponds to these corner points in the original problem. Okay? So as a result, basically there's a correspondence between corner points and basic feasible solutions. Okay? So that solution actually corresponds to this corner point. So as a result, this corner point can be expressed as a basic solution in the system. Okay? So that's important. Does everybody see that? Okay? All right, so now I'm going to look at all other possibilities as well. So, and I'm going to try to do this in a systematic way. So what else can I use as my basic variables? I start with x1 and x2. So let me continue with x1, x3. What are my non-basic variables then? So x2 and x4. What is my matrix B? So it's going to be given by the first and the third columns of A. Okay? So I'm going to have 1, 0, and 1, 0 again. What about n? So it's going to be second and fourth columns. So n is given by 1, 1, and 0, 1. Okay? But now let me look at my matrix B in this case. Okay? So can anyone see a problem? Matrices, what's the problem of B? Well, so, I mean, there are a lot of ways of saying this. For example, B has a 0, B has a row which is identically 0, okay? Or these two columns are the same, so basically the rank of B is equal to 1, right? So B has only one linear independent row or one linear independent column, basically, okay? And since the rank of B is 1, but not 2, what does that imply about B? It's not invertible. So basically this implies that B is not invertible. Okay? So what does that mean? Well, essentially that means that, so there exists no basic variable with x1 and x3 as basic variables. Sorry, there exists no basic solution, is what I meant. Solution with x1 and x3 as basic variables. Now let me just try to illustrate what that means in terms of this picture. Okay? So first of all, I'm setting x2 and x4 equal to 0, right, in the second example. So when x2 is equal to 0, that means I'm actually on the horizontal line here, right? If x2 is 0, I should be exactly on the x1 axis, okay? Then I'm also setting x4 to 0. Well, x4 is the slack variable corresponding to the second constraint, right? If x4 is equal to 0, then that means that x2 should be equal to 3, right? So then I'm looking at this line and this line basically, right? Okay? But the problem is that these two lines are parallel to one another, right? They never intersect basically. And since they don't intersect, I can never have a solution with x1 and x3 as my basic variables. Okay? So that's the correspondence between, not having a basic solution and the fact that these two lines are parallel to one another. Okay? So these two lines never intersect. So as a result, they can never form a basic solution. Okay? Or they can never form a corner point basically. Does everybody see that? Okay? So as a result, I can never have a solution in which x1 and x3 are basic variables because those two lines never intersect and they can never form a corner point. Okay? Does everybody see that? Okay, good. So let me continue with other choices. So what else can I have? So I'm going to do x1, x4. So my xp is given by x1 and x4. And my xn will be given by x2 and x3. What is my corresponding B matrix?
1, 0, 0.
So it's going to be the first and the last column of A, which is 1, 0, and 0, 1. What is the N matrix? So it's the second and third columns of A, so which are 1, 1, and 1, 0. Okay, so I'm going to set xn to 0. Then my xp, which is given by x1 and x4, will be given by b inverse times little b. What's the inverse of b?
Invertible.
Well, b is the identity matrix, right? It's a very invertible matrix, right? Sorry?
Determinant of B is 0.
Is equal to 1.
Ah,
Okay? I mean, this is the identity matrix, the simplest invertible matrix, right? So B inverse is the same as B itself, of course. So this is the same as little b, and little b is equal to 6 and 3. Okay? Now, what does this solution look like? So x1 is equal to 6, x2 is equal to 0, x3 is equal to 0, and x4 is equal to 3. Let me just go back to my picture again. So if I, first of all, again, note that all the variables are non-negative. Okay? So which means that this is a basic feasible solution. Okay? And if I look at the first and second components, x1 is equal to 6 and x2 is equal to 0. So what does that correspond to in this picture? Well, that's exactly this corner point, right? Okay? So I'm going to call this number 3. Okay? So does everybody see the connection between basic solutions and corner points? So, this was the basic solution corresponding to this corner point. The third one, that basic feasible solution corresponds to this corner point. And let me just quickly do the rest. So what are the other choices for XP? So now, again, I'm going to do it in a systematic way. So I tried all possible combinations with x1. So now I'm going to start with x2. So I can try x2 and x3. In which case, xm will be given by x1 and x4. So what's my matrix B in this case? So it's going to be the second and third columns of A, right? So which are 1, 1, and 1, 0. What about N? So N is just the identity matrix, 1, 0, 0, 1. Is B invertible? Yes, it's an invertible matrix. The columns are linearly independent, so it's an invertible matrix. I'm going to set xn, which is x1 and x4, equal to 0. Then my xp, which is given by x1 and x4, will be given by b inverse times little b. So b inverse is given by 0, 1, 1 minus 1. And I'm going to multiply it by little b, which is 6, 3. Okay? So what do we get? Well, I guess we get 3, 3, right? Okay? All right, so what are the values of my variables? Well, x1 is equal to 0. What about x2? Sorry, I made a mistake here. So this is x2 and x3. The value of x2 is equal to 3. The value of x3 is equal to 3 as well. And the value of x4 is equal to 0. Okay? So the corresponding solution in the original picture is given by 0 and 3. So x1 is 0, x2 is 3. Well, surprise, surprise, we get this corner point right here, okay? So since all the variables are non-negative, again, this is a basic feasible solution. Are we done? So have you looked at all possibilities? No, not yet. So I can also have xp is given by. So what's the next possibility? I can try x2 and x4. xm will be given by x1 and x3. What's my corresponding matrix B? So it's going to be the second and the fourth columns of A. So it's going to be 1, 1, and 0, 1. What about N? N is given by the first and third columns, which are 1, 0, and 1, 0. I mean, one important thing is that note that we only care about the matrix P. So the matrix N does not have any role at all. Okay, so we care about only invertibility of matrix P. All right, so I'm going to set all the non-basic variables to 0. x1, x3, I'm going to set them 0 to 0. Then my xp will be given by x2 and x4. So I'm going to have b inverse times little b. And what's the inverse of b in this case? So it's 1, 0, minus 1, 1 times little b. So what do we get? Six and minus 3, basically, right? So we get 6 and minus 3. Well, so what's my corresponding solution? x1 is equal to 6. x2 is equal to, x1 is equal to 0. Okay. x2 is equal to 6. x3 is equal to 0. And x4 is equal to minus 3. Well, is this a feasible solution? No, it's not a feasible solution because x4 component actually violates this requirement, right? So this solution is not feasible. So it's still a basic solution, but it's not a feasible solution. Okay? So since it's still basic but it's not feasible, it's not a basic feasible solution. Okay? So this is not a BFS. Let me go back to my picture again, and let me try to see what's going on here. So what's the value of x1? x1 is equal to 0, and the value of x2 is equal to 6, right? So what does it correspond to in this picture? x1 is 0, x2 is equal to 6. It actually corresponds to this one right here, okay? So the thing is, it's still a corner point, but it's not a corner point of the feasible region, okay? So it's still the intersection of two lines, but the problem is that that point does not lie in the feasible region. So as a result, that basic solution is not feasible for our problem. Okay? So it still corresponds to the intersection of two lines, just like all the other examples that we have seen so far. But the problem is that, that solution is not feasible for our problem. Okay? So as a result, we have a basic solution which is not feasible. Okay? So which means that not all basic solutions will be feasible, basically, right? So some of them may be infeasible as well. Okay? So there's one last possibility. Let me try to squeeze it here. So what's the final possibility? So xp will be given by x3 and x4. xn will be given by x1 and x2. What's the value of B, matrix B? So it's going to be given by the third and fourth columns of A, which is 1, 0, 0, 1. What about matrix N? So it's going to be given by the first two columns, which are 1, 0, and 1, 1. Then I'm going to set xn to 0, and I'm going to solve for the basic variables. I have x3, x4, which is B inverse times B. Well, B is just the identity matrix, so its inverse is equal to itself. So this is the same as little b. Little b is equal to 6, 3. So as a result, my solution is given by x1 equals 0, x2 equals 0, x3 is equal to 6, and x4 is equal to 3. Is this a feasible solution for my problem? Yes, it is. So as a result, this is a PFS. Now, which solution does it correspond to in that picture? The origin, exactly. So as a result, this is the solution, this is the corner point corresponding to the basic feasible solution. Okay? Now, what's the point of all this discussion? Well, the point essentially is the following. So there's a one-to-one correspondence between basic feasible solutions and corner points. Okay? So basic feasible solutions give us exactly which points are corner points. And conversely, every corner point is a basic feasible solution. Okay? And remember, so a couple lectures ago, we posed the following question. So if I give you an LP problem in 100 dimensions, how can you say whether a given solution is a corner point or not? Well, from now on, we can actually use this characterization of corner points, okay? So this characterization of corner points actually does not need the geometry, okay? So we can simply say that if we have a basic feasible solution, then we know that that's a corner point, okay? And conversely, every corner point corresponds to a basic feasible solution, okay? So as a result, using this definition, we no longer need to see what's going on geometrically, okay? So we have a characterization of what corner points look like. Does that make sense? Okay. Let me just give you final remarks, because I don't want to sort of break this later on. So this system has 5 basic solutions, but only 4 basic feasible solutions. So remember, one solution, which is solution number 5, was a basic but not a feasible solution, basically, okay? And one solution for one possibility, B, was not invertible, so as a result, we had to get rid of that possibility. So the feasible region has 4 corner points. So which means that we have 4 basic feasible solutions, we have 4 corner points, so there's a one-to-one correspondence basically, okay? So each PFS corresponds to a corner point, and conversely, each corner point corresponds to a basic feasible solution. And as I said, I mean, the nice thing about this is that, so now we no longer depend on the geometry, okay, to characterize corner points. So we can just use the definition of basic solutions. So whenever we have a system, a problem in standard form, and if we have a basic solution which is feasible at the same time, then we know that that's a corner point, okay? And the thing is that, so this characterization is great because now you can sort of think about LP problems with any number of variables, okay? So you don't need to see what's going on geometrically, okay? You can define a basic feasible solution even if you have 100 variables, okay, by using the same procedure, okay? And in fact, you know, when you do your projects, this is exactly what the solvers like Excel and Express and so on and so forth actually do, okay? They use this characterization of corner points. And we can also see later on how we can use this characterization to develop an algorithm, basically, okay? Any questions? So at least, I mean, is it clear that now we know what corner points are for any general LP problem? So is everybody convinced? All right, so I'll see you next time, okay?